joining the meeting today. This is my pleasure to introduce today's distinguished speaker, Dr. Vijay Singh. He has many achievements, and I cannot list all of them. He is currently a Regent Professor as well as inaugural chair in water engineering at Texas A&M University. He's a member of National Academy of Engineering, and he has published. I was reading his bio, and he has published 1,630 refereed journal articles. So that gives you breadth as well as depth of his knowledge base. So with that, I think this community very well know Dr. Singh's work. So I'll let Dr. Singh to take the stage, and he's
And
going to
let
talk about
me,
hydrologic modeling theory and practice. Thank you.
okay, thanks, Sanjeev. Okay, okay. Okay, so today we will talk about hydrologic modeling, and basically I will try to show you how various kinds of hydrologic models can be represented under a unified framework. And so, but before we do that, it will be interesting to take a look at the historical perspective. And before that, let's take a look at the hydrology itself. So it is always a good idea to go back to the basics. So if we anatomize hydrology, then you will see that there are basically four components which essentially delineate the domain of hydrology. Of course, we start out with water, but water is characterized by both quantity and quality. And really, these two aspects cannot be separated from each other. They should be treated in tandem. And of course, there are four phases of water, even though normally we discuss three phases, liquid, vapor, and snow, which is, that's a liquid, gaseous, and solid. But there is also a fourth phase. And then the third component is where water occurs. So basically, it occurs only in three domains, either over the land surface or below the land surface in unsaturated zone or in the saturated zone. And there are three domains within which this occurrence takes place. In other words, it occurs either in a space or time and the frequency. But also the occurrence takes place at different scales, ranging from micro to meso to macro to mega. And essentially, there are only four processes through which water occurs: the occurrence, distribution, movement, and the storage. And this, so let me, I think, take this thing. Okay. So essentially, okay. So there are really the hydrologic processes essentially can be classified into two: the storage processes and flow processes. The storage occurs essentially either over the ground or below the ground, but it occurs in the atmosphere, and that occurs as interception storage, depression, detention storage, channel storage, storage in lagoons, lakes, reservoirs, wetlands. Water is also stored as snow, ice, and glaciers. And then the flow processes essentially take place either on the ground or below the ground. So on the ground, essentially, then water moves either vertically downward or, for example, water moves vertically downward as precipitation, upward as evaporation and transpiration, and then, of course, downward as through flow. And water also moves horizontally as overland flow, channel flow, and glacial and snowmelt. And in unsaturated zone, it particularly, actually, predominantly, it occurs vertically downward as infiltration and percolation, but also it can occur horizontally as interflow. And of course, in saturated zone, the dominant component is groundwater, which occurs horizontally, and the same thing occurs as base flow. But in saturated zone, water also occurs vertically downward, if particularly in the case of leaky confined aquifers. So with that, I think we take a quick look at the historical developments that have occurred. If you go back in history, then one can easily trace the beginning of mathematical modeling of hydrology to the year 1850. So in the case of surface runoff modeling, the first mathematical framework was developed in the form of rational method by Mulvaney in Ireland in 1850. And then, of course, the peak discharge, where essentially the main hypothesis of the rational method is the peak discharge is a function of rainfall intensity. And the same thing was pretty much done in France in 1892. Then, of course, almost 80 years later, the unit hydrograph method was developed by Leroy Sherman in Chicago. And this method is essentially based on two principles, principle of proportionality and principle of superposition. And this unit hydrograph method essentially can be without exaggeration, be characterized as the origin of hydrological systems. Then in 1944, Quilligan developed the overland flow analysis using hydraulic principles. And Wizard, who was a road engineer or highway engineer, did some experiments on road pavements in 1944 that essentially developed the empirical analysis of overland flow because he did experiments on pavements and through which he derived an empirical flux concentration relation. In 10 years later, Eamon Nash and Jim Doos developed the unit hydrograph theory, which was essentially the extension of the unit hydrograph method developed by Sherman, but they provided the mathematical framework and also provided a lot of physical insights into the theory. And that is essentially that was based on the concept of instantaneous unit hydrograph, considering the cascade of linear reservoirs, time area method, and network of linear channels and reservoirs. Then we go back to again, so that was essentially those methods were describing the time history of discharge, particularly surface runoff. But surface runoff, in the area of surface runoff, also in 1935, Horton actually developed flow depth relation using his experiment that he conducted in 1935. And then, of course, Iwagaki in 1955 developed diffusion wave theory for essentially for flow routing in channel. In 1955, or the same year, two mathematicians, Mike Lytle and Garvis Witham from the University of Manchester, developed the kinematic wave theory, which essentially is based on, besides the continuity equation, two principles, flux concentration relation and shock formation. And then in 1979, Ignacio Rodriguez and his associate Valdez developed the unit hydrograph theory, the geomorphologic unit hydrograph theory. Basically, the geomorphologic unit hydrograph theory essentially uses the essentially using the same unit hydrograph theory, except that it couples with a simple framework of representing a watershed through a network of linear channels and overland flow planes based on essentially the geomorphologic principle. This is an experimental facility that Horton developed in 1935. Horton has his own laboratory where he did all kinds of experiments. He was a very, very high-level theoretician. He did all kinds of experiments. Now let's move on. This is another in 1966. Venti Chow also conducted experiments in the laboratory in 1966. This is Hydro Systems Laboratory. Even now, it exists at the University of Illinois in Urbana-Champaign. So, but anyway, these works essentially were for describing the entire discharge hydrograph. But the unit hydrograph theory cannot be applied without knowing the runoff volume that will be generated by a given rainfall event. So the Soil Conservation Service, which is now called as the National Resources Conservation Service, NRCS, in 1956, essentially developed a method which is popularly called as SCS-CN method. CN is for curve number. And this is based on the proportionality hypothesis. I know a lot of hydrologists really disregard this as entirely empirical, but I can tell you that so far we have not come up with a better method for computing storm runoff. And this method is not entirely as empirical as a lot of people tend to think. Then in around the same time, Army Corps of Engineers actually wrote a treatise uh, under the title of snow hydrology, which is still a landmark contribution. So they developed all kinds of relations for snow melt runoff, particularly the degree day factor. That is, that method was developed in 1956. On the other hand, so that was, all this was confined to surface runoff modeling, considering both the time distribution of discharge as well as the runoff amount. But then the theory of infiltration was developed by Green and Emd, and now it is called as the Green and Emd infiltration model. That was in 1911, which was based on the principle of piston movement. And Kostyakar developed an empirical relation in 1932. Then, of course, the Richardson, now popularly called a Richards equation. In 1931, he derived a diffusion equation for describing the movement of soil moisture uh, in unsaturated zone, which essentially which is based on the coupling of Darcy-Buckingham law and the continuity equation. But in 1933, Horton also derived an infiltration equation, which is popularly called as the Horton equation. On the other hand, the theory of evaporation, Horton also derived an evaporation equation, which is based on physical principles in 1917. Unfortunately, a vast majority of people are not even familiar with Horton evaporation equation. And then, of course, in the energy method for computing evaporation from water bodies or saturated medium was developed by Richardson in 1931, Cummings in 1935. And then, of course, Penman. Penman was a physicist. He combined the energy method with mass transfer method. And that's why it is called as the combination method, which is essentially a combination of these two principles. And this is, the Horton's infiltration experiment that he did. And of course, the subsurface flow modeling was developed by Loudermilk in 1935, which described the subsurface flow mechanism. And then, of course, later on, several other people followed. In 1970, Tom Dunn and Black developed partial area contribution of saturated flow mechanism. So now you see there are three mechanisms: rainfall access mechanism developed by Horton, subsurface flow mechanism, and partial area or saturated flow mechanism for the generation of steam flow. Then, of course, there were also developments related to modeling of different hydrologic components. For example, interception, Horton derived an empirical model in 1919. Then SCS in the Soil Conservation Service in the development of their SCS-CN method also empirically modeled detention and depression storage in 1956. Then, of course, groundwater. Really, the basis of groundwater hydrology is the Darcy equation, 1854, which was derived. Some people say it was 1852, but somewhere around that time. And of course, Fair and Hedge derived an empirical relation for hydraulic conductivity, which essentially says that that permeability is directly proportional to some power of average grain size diameter. And then, of course, the real breakthrough came in 1935. Charles Thies, who derived the well response to pumping, which is essentially nothing but the diffusion equation. And also then Cooper and Jacob, they derived a method for aquifer parameter estimation, which are essentially transmissivity and storativity. And it is popularly called as the Cooper-Jacob method. Sometimes people call it Jacob method. But they also established a correlation between groundwater and precipitation, which formed the basis of groundwater recharge. It was an empirical study, but very good study. And Chow also in 1952 developed a method for estimating transmissivity and storativity. It was a graphical method, but it is popularly used, and it's called the Chow method. And for leaky aquifers, Mehdi Huntush and C. Jacob essentially developed a parameter estimation method, the same parameter, but for leaky aquifers. Then, on the other hand, for flow routing, particularly in reservoirs, the U.S. Army Corps of Engineers in 1928, they developed the pulse method and the volume balance. And then, of course, the U.S. Bureau of Reclamation modified the pulse method in 1949. But these are essentially volume-based method. Then in 1935, the Muskingum method, the McCarthy developed. Muskingum is actually the name of the river basin in Ohio, but now it is popularly called as the Muskingum method. McCarthy was the one who developed this in 1934, 1935. It is essentially based on the linear hypothesis, and also U.S. Bureau of Reclamation modified the reservoir pulse method for channel routing as well. Then on the frequency domain, the 1951, the Gumbel, which is called as the Gumbel distribution, Gumbel actually derived using the extreme value theory, the extreme value type 1 distribution, which is popularly called as the Gumbel distribution. In many countries, the Gumbel distribution is still used, even though, and then of course, 1951, Chow derived the frequency factor method for doing frequency analysis. Then in 55, he developed the long normal frequency factor table. And in 1952, around the same time, Hurst, now it is popularly called the Hurst exponent, which is essentially for the predictability of the time series. So what I'm saying is, if you notice that there are certain periods during which a lot of developments occur, particularly, say, for example, around, in the first part of the 50s, or around the 30s, or right in the beginning. And in between, there were very few developments that occurred. Now, coming from India, I might argue that I think this has something to do with the star configuration. Of course, that's a matter of debate anyway. So where do we use all this? Actually, there are two types of hydrologic applications that one can categorize. First, the design problem. Design means we size the system. For example, we size water supply scheme where we need to compute the volume of time, runoff, the time, the frequency for drought, for risk assessment. Likewise, for drainage design where you need peak discharge, again, frequency, risk, damage assessment, spillway and dam design, likewise, design of soil conservation structure, highway pavements, culverts, bridges, rehabilitation of aging dam. In all of these, either we need the volume, but mostly peak discharge, frequency, risk, and even losses. But there is another category where also hydrology comes into play very prominently, which are essentially non-design problems like pollution abatement, where we need space-time distribution of pollutants movement or risk, or ecological sustainability for watershed models we use for flooding, drought, watershed management, restoration. climate change impacts, for example, we need erosion control measures, we need sediment deals, soil conservation measures, erosion, sediment. Here you are not necessarily constructing any hydraulic works, but you still need hydraulic. Likewise, there is a very large range of problems. We will not worry about all this. So, having said this, now I will show you that essentially there are three principal theories which I believe that we use in hydrology. And under using these basic three theories, a lot of these models that I've just briefly touched upon can be brought together under one umbrella. So there are three basic theories, either system theory, wave theory, or entropy theory. Now, the system theory essentially is based on two fundamental principles, especially lumped form of continuity equation, linear or nonlinear flux concentration relation. And wave theory is based on essentially three principles: distributed continuity equation, nonlinear flux concentration relation, and the law of shock formation. And then, of course, the entropy theory is based on four essentially principles. First, we have to define entropy, and the reason we put entropy definition as a first component is because entropy is defined in different ways, and there are many definitions of entropy. We'll not go over, we'll use only one definition. The second one is the principle of maximum entropy, third one is principle of minimum gross entropy, and the fourth component of entropy theory is theorem of concentration. And I'll show you that many of these models that we have briefly discussed can be derived using some of these theories. So let's take the system theory. So the system theory, as I said, it is based on the spatially lumped continuity equation. So if you consider a reach or in a particular segment of a watershed, then you can derive here the flux is psi and phi is flux and psi is concentration. So you can actually, this is the spatially lumped form of continuity equation, where x2 is the output, x actually the location at which output is occurring in the form of concentration, and and of course this is the x1 corresponds to the either upstream area, that is the downstream area. So that, for example, take the case of unit hydrogram. In the unit hydrogram, a linear reservoir is described by storage as a direct function of discharge, where the proportionality is represented by K, which is really nothing but the lag time or the average residence time. Linear channel where the storage essentially is constant. In other words, there is no change in the storage, which means whatever you put in, the same thing comes out at a later time. If you consider the Muskingum method, which is again is a linear law, except it says the storage is a linear weighted function of inflow and outflow. So the weight is measured by this parameter x, which is nothing but which is between 0 and 1 theoretically, but practically it is between 0 and 0.5. Now, let's take the case of infiltration. And I want to show it because this is more complicated. So the spatially lumped form of continuity equation, as I showed you, and then you can define a nonlinear algebraic flux law. So here the flux is the infiltration rate and concentration is the cumulative infiltration. So if you take an Fs here is the steady state, S0 is the proportionality constant, and S naught is nothing but the maximum soil moisture retention capacity, which is equal to porosity minus plant roots, earthworms, and so on. So you can see Ft minus F is directly proportional to S0 minus Ft raised to the power n over Ft. Now you can see that this has a physical meaning because you are saying that the infiltration rate is directly proportional to whatever space is available. If there is more space available, you will have higher infiltration, and inversely proportional to what has already taken place before. So, it is actually identical to the way people eat or your appetite. And now, so if you couple this with the continuity equation, then you can see if n is equal to 1, m is equal to 1, leads to the Kashikov equation. If n is equal to 1, m is equal to 0, it leads to the Horton equation. If n is equal to 0, m is equal to 1, fs is equal to 0, it leads to Green-Empty equation. Likewise, if m is equal to 0, f is equal to 0, it leads to Overton equation. And of course, if m is equal to 0, it leads to the generalized Holton equation. There are other infiltration equations with a little bit of algebraic manipulation. You can also derive Hughes-Monk equation, Phillips-two-term equation. So almost all equations, actually most equations can be derived using the same principle. Likewise, if you extend this to, to um, to nonlinear reservoir, then of course you can get nonlinear Muskingum method. Now, of course, if you can also express the rating curve in the same way or the sediment delivery in the same way, you can describe internal erosion in the same, exactly the same. So what is different? What is different from one component to the other? It's only flux conservation. The continuity equation is not changing. Now, the second one is again the second aspect of system theory, the proportionality theory. Proportionality theory, as I said, which was the basis of the CSCN method. So, what does the proportionality theory says here? I think this is a point worth understanding. What this says is, if you take the design variable, in this case is Q. Now, note here, Q is not discharge. Here the Q is the amount of direct runoff or surface runoff, which will be generated by a precipitation event. So the design variable divided by the maximum value that the design variable can take, which is precipitation minus whatever the abstraction is. So if the soil is completely saturated and there is no infiltration, obviously the maximum value of Q will be nothing but P minus IA, where IA is nothing but abstraction. So this proportionality hypothesis says the ratio of the design variable to the maximum value equals the ratio of the control variable divided by the maximum value of the control value. So here the primary control variable in the case of surface runoff is actually infiltration during a precipitation event, because the evaporation is almost negligible. So the only abstraction is essentially, is the main abstraction is nothing but infiltration. So the volume, the cumulative amount of infiltration, which can take on the maximum value is equal to the porosity or the maximum soil moisture retention. This is the proportionality hypothesis. Now you can also apply the same thing, the same hypothesis to subsurface drainage, the same hypothesis to evapotranspiration, the same hypothesis to sediment yield. And these are the proportionality relations I'm enumerating. For shortage of time, let me. Now, what is interesting is you can also apply the same hypothesis to deriving frequency distribution. So in case of frequency distribution, the continuity equation is really nothing but the derivative of CDF, which is the cumulative distribution function, which equals the probability density function. So the proportionality relation in this case is, look at the flux, which is f of x or df over dx, is directly proportional to the cumulative distribution function and 1 minus, which is the survival function, which is raised to the power n. So you can intuitively feel that the probability density function will be higher if the event has not taken place. And it will be lower if the event has taken place. And so basically here, that's what 1 minus f of x is the survival function says. So if n is equal to 1, n is equal to 0, so here the key is how to express this proportionality function, because the proportionality function in this case is not a constant. So g of x, for example, if you take it this way, this will lead to extreme value type 3 distribution. And you can derive any distribution, provided it is expressed in explicit form. For example, extreme value type 1 distribution, if m is equal to 1, n is equal to 0, and g of x is this way, it leads to extreme value type 1 distribution. If n is equal to 1, n is equal to 0, and g of x is written this way, it will lead to Weibull distribution. Likewise, you can derive Pareto distribution, you can drive generalized extreme value, you can drive almost any distribution. Now let's go to now the second one, which is the wave theory. Now in wave theory, of course, there are three types of wave theory. Of course, many wave theory from a hydrologic viewpoint. Actually, there are only the diffusion wave, kinematic wave, or dynamic. But the most versatile is really kinematic wave. Diffusion wave has restricted applications, particularly in the case of routing in channels and even reservoir. Or it has also an application if you want to drive the pollutant transport. Uh, so, so let's focus only on kinematic wave theory. So the kinematic wave theory, again, the concentration here, C, and of course, capital F of X, here in this case is flux, and C is concentration, and I is nothing but the input function or the forcing. So if you take this, and then, so basically the wave theory essentially prescribes a function between C and F. And then of course there is a law of shock formation, which is really which describes the shock velocity, which is equal to the ratio of the difference between the flux before the shock and after the shock divided by the concentration before the concentration of flow. So the concentration of flow in this case will be nothing but depth. So concentration before the shock and after the shock. So in case of surface hydrology, for example, for discharge hydrograph, we use Q, which is the flux, is directly proportional to the flow depth raised to some power n. Now, of course, from hydraulics, n can vary from 1 to 3, depending upon the quality of flow. In irrigation hydrology, this is expressed as the flux is expressed as a function of cross-sectional area. In Wardo zone, it is expressed Q, which is actually flux per unit area, which is like a velocity, which is directly proportional to the hydraulic conductivity as a function of capillary potential or moisture content. Remember, K, unlike the Darcy equation where K is constant here, K varies with the degree of saturation or the moisture content. The same thing applies to the same principle actually applies to snow and glacier melting, and also we can do for water quality hydrology. Now, of course, the entropy theory, as I showed you, the entropy theory essentially has, you can enter all, there are two types of problems that we have. First, we can drive probability distribution, but we can also drive physical and empirical relations using the entropy theory. Now, if you want to drive the probability distribution, you can drive any probability distribution using entropy theory, provided the restriction is provided the distribution is expressible in explicit form. And here we can use the Shannon entropy, which is by far the most versatile and robust entropy definition. There are others. For example, so if you drive the entropy theory, the key here is to specify the constraint. Constraints in the case of entropy theory are analogous to, in statistics, what we call a sufficient statistic. So you do entropy maximizing using the Euler-Lagrange calculus of variation. And then, of course, you can drive the distribution parameters in terms of the constraint that you express. So in that way, the entropy theory obviates the need for parameter estimation because you are expressing the distribution parameters in terms of the information that you are codifying. And for example, you can drive the generalized extreme value distribution provided, these are the two constraints that I'm describing here. The same thing you can drive essentially the generalized gamma distribution, generalized beta distribution, and we have done the comparison, and theory works really well. But you can also drive physical relations. Not only you can drive the frequency distribution, but you can drive physical. For example, you can drive a generalized instantaneous unit holograph using the entropy theory. Suppose that your constraint is the geometric mean and the power mean. So say geometric mean is nothing but the integration or log of time of travel multiplied with the IUH, which is, so the instantaneous unit hydrograph is analogous to the probability density function. And doing a little bit of algebra, you can see that you get a very generalized IUH expression, which specializes into gamma distribution, linear distribution, Nakami distribution, exponential, Biver, Raleigh, Maxwell. The gamma distribution is frequently called as the Nash model. So you can do that, and without doing any fitting, this is just an illustration. Okay, but if you want to drive the physical relation, then I think we need to specify a fundamental. We have to specify a relation between flux and concentration. Only then we can move from probability domain to the real domain. And so these are the flux constant relations which I have used, which are quite generalized. Now, for example, you want to drive the SCSCN method using the entropy method. So SCSCN method, as I said, the volume balance and the proportionality hypothesis. You do a little bit of algebra and you find actually in a few steps exactly the same SCS method. So the question one might ask is, so what? The advantage of so doing is that the entropy theory allows you to specify the distribution, the probability distribution of the discharge or the amount of discharge that you get from the SCSCN method, which means you can also specify the uncertainty bounds, you can specify the rates, and so on. So you get a lot more than simply driving the method or the relation which the SCSCN method already does. That is the advantage. Now, of course, you can, I have derived all kinds of implication equations, Horton, Kashikov, generalized, Smith-Parlan, Philip-Tudor, using the entropy theory, almost all these popular. And this is an example of Horton method. And so I will not go over because I'm running out of time. So the same thing, actually, you can also apply the entropy method to drive the soil moisture as a function of depth, because the soil moisture in the horizon, and then you can also express the time history of soil moisture. Now, in case of soil moisture, remember, there are three phases: the wetting phase, the drying phase, and the mixed phase. So for the wetting phase means here the saturation front is moving from the land surface down below. In the drying phase, it is the other way around. But in the mixed phase, it can be both ways. You can have a drying front and then it meets the saturation front. Or you have a saturation front and then it meets the drying front. And you can drive actually using the entropy theory, which is what I've done here. And what is interesting is that without doing any fitting whatsoever, we took the data and you see it seems to work quite well. And then, of course, if you couple this derivation with the volume balance, then you can drive the soil moisture time history, which is what I've done over here. So there are, you can also drive the sediment yield, for example, the sediment yield as well as the sediment discharge. So sediment discharge, first the sediment yield. So this is a relation like this, like the relation which has been quite popularly used between the sediment load, which is the vast load, especially which is true for upland areas or agricultural water set, which is directly proportional to the volume of runoff. You can drive this empirical relation, or you can drive exactly the sediment discharge hydrogram, which can be derived in two ways. Okay, so let me not go over. It can be derived in two ways. First, you can drive the discharge hydrograph like using unit hydrograph theory, and then you drive the concentration relation, multiply the two, you will get the sediment discharge hydrograph. Or you can also apply the same principle which has been applied to drive the unit hydrograph in the case of sediment discharge hydrograph. So what is the principle? There the principle is, remember, here the forcing is the erosion as a function of time. And the instantaneous unit sediment graph, which is analogous to instantaneous discharge hydrogram. Then if you do the integration, using the Green's function, then of course it becomes a discharge hydrogen. Or you can do, as I said, by simply driving the discharge and the concentration separate. And so this is the sediment yield and this is the sediment discharge hydrogen. Anyway, now if you combine all these components, then of course here actually I want to make only one point, and that is in the beginning there was emphasis on component modeling. Then, of course, beginning with the advent of computers in the middle 60s, then, of course, the watershed models started getting developed, particularly with the beginning of the Stanford watershed model. The second row essentially describes the model sign. So emphasis was not only that is thereafter, that is in the late 60s and the 70s and thereafter, the second component is model science, which means the hydrologic models were integrated with water quality models, with sediment, with nutrients, and so on. And this was triggered also partly by the third column is by legislative mandate, because legislations were passed at the central level as well as the state level. The fourth column, which is now perhaps one of the most important column, is the computing technology. So it started becoming popular. Now, of course, we have all kinds of computing technology. This is the timeline of models, their component, like a kind of chronology of recent year. Let me not go over. Now, but we have now the capability to incorporate spatial variability of watershed characteristic, spatial variability of inflow, precipitation, and so on at different sizes. Okay, so having said all this, so what are now the current challenges? The current challenges are that actually we are the current challenges are the hydrologic model in many cases need to be developed at a much finer spatial scale. On the other hand, we also need models at the larger scale, at the regional scale, even at the national scale. And they have to be coupled with uncertainty analysis. And the question which is still nagging is the long-term forecasting. And also, we still really don't quite have as satisfactory handle on probable maximum precipitation. We don't even know how to properly define it. I mean, of course. Then, of course, these models have to be integrated with biogeochemical models, climate models, coupled systems, and so on. So and of course, the challenges are the models must be user-friendly. There must be model choices so that they are credible, and their credibility must be objectively and quantitatively specified. So that will take us to scope out the entire hydrology. Now, of course, we have several areas of hydrology which are emerging, like space, global, climate change, social, operational, and disaster hydrology. So the outlook is we will need more. There will be increasing demand by society for these models. There will have to be increasing emphasis on linking these models with environmental and ecosystem models. There will have to be an increasing emphasis on user friendliness. Models will have to incorporate information technology, computer-based design, artificial intelligence, space technology, and the models will have to clearly state uncertainty and reliability. Only then the model will be competitive. So we have to take a stock of the current situation, recognizing social and cultural constraints, and we have to take into account the looming global changes that are occurring. And of course, that will take us to re-examine and revalue our entire value system. So which means the future can be as bright or dark, it's all in our hand. So with that, I think I will stop here because I want to at least give you 10, 15 minutes of time for questions and answers. So with that, thank you all very much for indulging and for taking your time out to listen to me. It has been a kind of a quick brush because the 1 hour is really too short a time. So Prakash.
Yes, yes, Dr. Singh. Well, thank you very much. This was a wonderful presentation, a lot to unpack, and luckily we're recording everything. We're going to be posting that online, And
if anybody needs, I can even send the PowerPoint. That's not a problem. I can send you can distribute.
yes, I can take care of that. Well, let's open it for questions. Sanjeev, if you have any question, I'll let you go first because I know you need to leave.
I had one question, Dr. Singh. What
Yeah.
is your take on community modeling? Like, do we need one community model, or do we need several different individual models?
I think, remember, in hydrology, we deal with the natural systems. So, there are models which will apply across the board. But at the same time, there are a lot of other considerations which have to be taken into consideration. And that is when you say community, basically, this directly implies, in my mind, the human dimension. And once you integrate the human dimension with hydrologic models, then then you have to be community specific because the human factors have such a large diversity that they are not the same, even in the same area. In the same area, for example, you take the case of India, in the same area, the people in one community view things very differently from the people in another community. The people in rural areas have a very different frame of mind than the people in urban area. So the hydrologic components also accordingly change. For example, if you are dealing with urban community, there the problems are of very different kind because they are the the conveniences that people have, the pollutants which they generate, the waste material which they generate, they are very different. The natural hydrology will be pretty much the same. For example, the precipitation may not be changing that much. Of course, there may be heat island impact. That's a different story. But infiltration will be very different in urban area than in rural area. And so I think it is better to address the problems on a community level, taking into consideration the specific characteristics of that community. That's the way I would suggest to go.
Thank you. Prakash, you can take now.
Okay, great. Thank you very much, Sanju. Dr. Singh, I think I have one comment, and maybe then you can elaborate on that.
Yeah,
On one side, when you showed all these development of the models and at the same time the computing capacity,
yeah.
I think one interesting thing would be that we're also in an age where we're actually collecting a lot of data,
Yeah.
Remote sensing, uh, an extended network of rain gauges and everything, stream gauges. Integrating that would be also one of the important challenges.
No, but you are right. I had a slide on that, and in the computing technology, actually, we didn't have time to discuss in detail. But besides, computing technology is also driving not only the collection or acquisition of vast amounts of data, but also computing technology is responsible for development of database management. Computing technology is also responsible for all these IT-based technologies like ANN, artificial intelligence, machine learning, and deep learning, and so on. So you are right. I mean, these the data collection is becoming uh, so extensive, and at the same time is so important that fortunately a lot of hydrologic models are now taking advantage of this extensive data collection, particularly when we talk of quantifying the impact of climate change. You see, people are taking advantage of satellite-based, remote sensing-based data. Now, of course, the computing technology has also enabled us to develop all kinds of geographical information system. So you are right, but I would also say here that many hydrologic models. Okay, let me go back. You have to look at the problem that you are interested in addressing. there are all kinds of problems which really do not require extensive, large-scale remote sensing based data. On the other hand, there are areas where there are no data at all, and remote sensing data, remote sensing technology, especially satellite technologies, is enabling us to acquire data. For example, sitting here in the United States, we can get a pretty good idea about the discharge that is occurring in one of the major rivers in India.
Yeah.
So you are right. I mean, this is opening new opportunities and new avenues for doing hydrologic modeling. But again, as I said, there are areas where you just have to look at the problem. So the question is, so let me give you my take is, let the question decide what we need and what we do not need. And it is a question that will tell us what data we need and what we do not need and what kind of model we need, that sort of thing.
Yes. I see a number of comments that people really, those who attended your presentation really appreciate the fact that you went through a review of the history of hydrology. As you know, I always love that part. So let me open the floor and see if there is anybody who's attending, if they have any question, and give them an opportunity to ask those questions. Or if you want, you can just type it, and I will read them for everyone.
I think if you go to the chat,
Yeah, I see people are saying that it's that it's
okay.
great, they enjoyed it. I don't see any question yet.
Okay.
Oh, I see one from Guta. Let me read this and I'll try to summarize. Climate science and risk. So there's a question, you know, that goes about all the different theories and models that you've talked about, and the question is, how do you envision these core theories adapting to addressing emerging challenges such as extreme events or data uncertainty in a way that balances physical understanding and the growing influence of data-driven techniques?
Well, you know, that's a very broad question. These theories, for example, you take the entropy theory. Now, entropy theory essentially does primarily two things, or it there are three types of problems in hydrology that entropy theory can tackle. First, either you know the first type of problems is where only the definition of entropy is applied. For example, you want to design networks, groundwater networks, surface water networks, rainfall networks, water quality, it doesn't matter. You can apply, and it has a very practical application. You can apply it on a very large scale. For the entire country, for that matter, you can actually, and you can not only you can evaluate the existing network, but you can also design. The second type of problems where actually you, in the same vein, you can derive the frequency distribution. So the frequency distributions, for example, you can derive the frequency probability distributions of extremes, extreme drought, extreme floods, extreme erosion, extreme pollution. It doesn't matter what that extreme is, or extreme precipitation, or extreme glacial movement. So, you know, then of course the theory allows you to not only derive the distribution, but also it allows you to say a lot more than that, because once you have the distribution, then you can quantify the uncertainty, you can construct confidence bounds, and then you actually that can be immediately integrated with decision support systems or decision making. So likewise, you can also derive physical relations, which I showed. Physical relations means not 10 relations at one time, but one relation at a time. And the theory allows you not only to physically derive the relations, which means you can physically interpret the parameters that will be imbued in those relations, and also it will allow you to quantify the uncertainty associated with that particular relation. So there are all kinds of things actually one can do. I think the nice thing about understanding the physics and at the same time mathematics is that it allows you to satisfy your physical curiosity. For example, I showed you the infiltration. Let's say take the case of Horton equation. Now, Horton equation actually, as you know, has like infiltration is really nothing but the saturation infiltration plus some constant, and the difference between initial infiltration minus the saturation, that is steady infiltration multiplied with the exponential of minus parameter k multiplied by t, the time, because you are computing infiltration as it goes. But there is a parameter k here. Now, what we normally do is we essentially compute the parameter k simply by fitting. But the infiltration theory is telling you that k here is really nothing but the average travel time, which is analogous to the lag time in case of surface runoff or the residence time in case of flow routing. So it allows you to physically interpret and then be better able to estimate the parameter k, because now it tells you that this is the amount of time that water will take to travel from the land surface to the base of that soil column. Now, which is what essentially you need for irrigation scheduling. If you know how irrigation scheduling is done, it is done whenever in the root zone, that is from the surface to the depth of the root zone, when the soil moisture becomes almost 50%, then you do the irrigation. And then you irrigate so that the moisture becomes almost around 80%. You don't necessarily do it, when it is oversaturated, you don't do that. So that means it allows you to, then you can compute the amount of time you should allow the water to saturate the soil to the extent that you would like. So these are the things that you can do. Of course, no technology can solve all the problem, but the technologies that we have are able to solve a wide spectrum of problems with the physical input. And that is really the point I was trying to make. If you use either the wave theory or the systems theory or the entropy theory.
Well, thank you very much, Dr. Singh. It's 3 o'clock here. We've reached the end of our time. I'd like to thank everyone who attended the presentation. Please note that this presentation is recorded and will be posted on the YouTube page. If you have any question, you can always email me, and when I get the slides from Dr. Singh, I know some of you have asked if they can get the slides. I will share them with you. Again, thank you very much, and looking forward to listening to you again. Bye-bye. I'll pause this recording.